Chemistry 242, Organic Chemistry 2, Carboxylic Acids and Derivatives, continuation. Gotta mute my phone. Hi, Tristan. Hi, gonna get on camera? Hi. We're gonna talk about carboxylic acids and derivatives today. Isn't that cool? Yeah? Alright, so hey guys, I need to get a... Can you go, buddy? I need to teach. I'm teaching now. Go ask mommy.
What do you need, buddy?
Alright guys, I'm going to go ahead and get a link from YouTube. It should be showing now, and then I will post it in the Discord, and then I will start. And then just like before, I will go ahead and tag these videos, the timestamp in the comments from when I start. Or I will go ahead and tag these videos. Oh my God. Are you trying to get me upset, dude? What are you doing? What are you doing?
I'm getting the tablet.
Just go. Jeez, man.
Is the bag on?
Yes, go upstairs and be quiet. Daddy is.
Alright, going to start here in a second. I did want to talk a little bit before I get started into the lecture proper. I got a jumping jelly bean in the background here. Let me make sure that he's understanding that I'm teaching now.
He's going outside. It's just
Yep, he's getting his shoes on to go outside and play while Daddy's lecturing. Bottle flipping. You gonna show me to do some caps? You can do some caps, buddy?
Yeah.
All right, let's see this. Make sure you get a video, right?
I don't have a camera and I have nothing to do that.
Okay. All right. Well, yeah, let me go ahead and get a few minutes before get started here. Make sure everybody's getting logged in. If anybody in the Discord seeing me talk right now? Well, hopefully I have an audience today. We are going to get started here shortly. The thing I want to... Okay. Oh, I'm getting spam now. So I guess you guys are seeing me in Discord. Yes, you guys are all seeing me. Okay. One of the things I want to talk about, I think I mentioned in a previous video, is while we're all at our locked in our homes, you guys definitely want to try your best to keep to your regular routine. Me personally, I get up in the morning, my normal, wake up at the normal time, roughly. I am sleeping about a half hour late than usual. But I'm trying to keep to my schedule, go to bed around the right time. The main thing that's slacking is I'm not really working out right now because, yeah, I'm stuck in the house. I would normally do a bunch of walking and stuff to kind of work out, get out there. Definitely not a good idea right now. You definitely don't want to be walking around right now. Basically, get up, shower, shave, get dressed in the morning, all that kind of thing. As if you were leaving the house, and that's helping keep me kind of sane. I'm still going about my daily routine, and then instead of going to my office and hanging out and working, I'm kind of just working out here. So, working at my desk at home with a lot of distractions. So, trying to adjust here. Anyway, before I get started into the lecture completely, do you guys have any questions about anything before we get started? Okay, you guys are just realizing that I'm trying to teach here and making all kind of noise in the background. That's where you guys started waiting until I started streaming to do stuff, right?
I was boiling eggs before bed.
Okay, whatever. Oh man. All right, so let me go ahead and just go ahead and switch gears here a little bit. So I'm gonna go ahead and get started. I just gotta move my keyboard out of the way. Wireless makes it useful. All right, so I went ahead and wrote out what I'm going to go over today. I don't think we're going to finish up the actual lecture today. I also improved the lighting, so it should be a little bit brighter, better images. But anyway, I'm going to go over these topics here. We're not going to finish the chapter, obviously. We have actually like 3 more topics to go. But I'm going to go over lactones today, reactivity order of different acid derivatives, how to convert acid halides into all the other derivatives, synthesis of amides, hydrolysis of them, and then we'll end with decarboxylation. The next lecture we're going to do is actually going to wrap up the chapter, and then I will do practice problems at the end of the next lecture. So I'll do practice as we go along, but our normal days where I would spend like a whole lecture doing practice problems, that'll just be part of the next video. So without further ado, let's go ahead and get started properly. So, all right. So we're going to go ahead and continue the discussion of Chemistry 242, organic chemistry, the continuation of the carboxylic acids and derivatives. Last time we did go over esterification. That was essentially how we took a carboxylic acid and reacted with an alcohol under acidic conditions, and basically how we convert that to an ester. The example I'm going to do here is a little bit different. I have notes here that I'm referring to. I'm just pulling them up. They're all the notes I'm referring to are actually posted on Canvas too, so you guys have everything that I'm looking at. Where'd it go? It should be after this page, right? There we go. All right, so let's go ahead and switch back to the document camera and let's get started. And fix my view on a few things. Hang on, fumbling with the software again. All right, there's that. Sorry, pardon me. I'm getting my view set up so I can see. And let's see how that looks. All right. All right, so the example I want to go ahead and work with, this is going to be a intramolecular reaction. So let's go ahead and take a look. So let's take that, and then I'm going to have an OH over here. And then on this end, I'm going to have a carboxylic alcohol and an acid in the same compound. It should come back online. Hang on. It should be back. It should come back. Hang on. Let me wait a second. It should come back. It's back. Okay. All right. Yeah, guys. If I ever go offline, typically I was dropping frames and the stream goes offline for a second. But if you're watching it after the fact, it's typically just fine. You don't get the frame drops if you're watching it after. So, all right. Anyway, what I was going on about was we are working with an alcohol and an acid, and we're going to show an intramolecular esterification. So what you want to do is you want to go ahead and start with protonation of this one. You could make arguments about this one maybe being more acidic, but it works out for the reaction to actually proceed. It's going to protonate from one of these. Let's see how the green arrows look on here. I normally do green arrows in lecture. I've been using red for the sake of the camera. Oh, that looks okay. All right, so we then go ahead and draw the result of that. So you want to keep counting your carbons too. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And then we still have an OH. We now have a protonated acid, like that. And then OH. If you're comparing it to the other mechanism that we did, this is the point where the alcohol will then come and attack the carbonyl. But instead of having a separate alcohol come in, it's going to be an intramolecular version of it. So one of the lone pairs on oxygen over here is going to attack, like so. I think now is probably the hardest part of a problem like this, is to make sure you get the correct ring out of this. So what I like to do is to number my carbons. 1, 2, 3, 4, 5, 6. So if you think about this here, we're going to have 5 carbons and oxygen as part of the ring. It's going to be a 6-membered ring with an oxygen in it. We saw something just like this when we were doing the acetal stuff. But instead of attacking an aldehyde, I'm having it attack a carboxylic acid. It's going to be kind of the same though. So 6-membered ring. So oxygen, and then we have our 5 carbons. What you could then do is add your numbers into here and make sure you're keeping track. So these 5 carbons are these 5. 1, 2, 3, 4, 5. And then notice here we have coming off carbon 5, we have a methyl group. The oxygen here still has an H attached. I'm going to highlight the new bond. The new bond is right there between oxygen and carbon 1. And then if you think about what we have here now, we have OH and OH. Like that. And don't forget we have a charge here, like that. The next step here is the end goal is going to be a ester. So we need to get one of these to leave and make a carbonyl at this carbon. The way we do that is a proton transfer step. So this is another example of a intermolecular proton transfer. And I'm going to use the same kind of shorthanding. Oop, hang on. My arrow is backwards. It should be from the oxygen to this one, like that. And then because this is technically intermolecular, I'm going to tell the reader that by showing that arrow push, like that. The reason why we do that is we now have a better leaving group. So oxygen, OH2, that is going to be a water leaving group, plus, and OH. One of the lone pairs here will then basically form a carbonyl. Oops, I was using green today. So push that down. When that happens, something has to break. So the best leaving group leaves at this point. So that knocks out. We have a water leaving group. And I'm going to bring it back in here at the end as well. Oop. Messed up my drawing. Oxygen. This next step, students will often forget. Don't forget that you still have an H on the. Why they're not showing up really good? Hang on, let me fix the lighting. It's like washed out or something. Hang on. Ah. Oh, it's looking worse. Yeah, let me just turn it off. Yeah, I think it looks better without the light. What do you guys think? Better with the light on or off? There's light on, and there's light off. I'm thinking it looks better with it off. What do you guys think? Yeah, it looks better with it off. Okay. Yeah, I tried. All right, yeah, everybody's saying off, so yeah, I'll go ahead and leave it off. All right, next step here, we're almost done, is your water molecule will then come in and just deprotonate. So deprotonate, like that. And then we get our final answer. Oops, gosh, I keep breaking the lead. That's not my best drawing there. Let me fix the drawing here a little bit. Gosh, I keep breaking the leads. All right, you got to go. And then for mass balance reasons, I'm going to go ahead and include H3O+. Remember, this is an H+ catalyst mechanism, so we're showing it being used, and we're showing it being remade. So we're good. All right, this kind of compound is called a lactone. Lactone, and this is basically a cyclic ester. Yep, so typically if you want to make a lactone, you want to do a intramolecular esterification here. And then if you wanted to, you could break this apart by a saponification to get back to the straight chain. Okay, are there any questions about lactones? This is just an application of the esterification reaction that we did last time. Check on Discord. All right, I'm not seeing anybody typing. Wait, someone's typing. It's lagging really bad? Okay, sorry if it's lagging. Waiting for questions. Hey, can you check if he's watching YouTube or something on his?
He's not. I turned off this tablet.
Okay, because like they're telling me I'm lagging.
I'll turn off my laptop.
Yeah, hang on. Let me put my. I think we have too many devices on my home internet right now, so I'm gonna go ahead and turn off my Wi-Fi on my phone. Yeah, everybody's turning off their devices right now, guys. So I know I'm lagging. So hang on. Sorry about this. Yeah, we turned off my devices is the best we can do, guys. Hang on, let me put it in the chat. I wouldn't be lagging in the classroom. You need to be back in the classroom. All right. I'm gonna go ahead and have to continue, guys. So hopefully it's better now. I'm hoping. Yeah, image is blurry. Fuck. Yeah, you may have to just come back later and watch it after it uploads. Okay. All right. I'm gonna go ahead and continue. Sorry about the lag, guys. I don't know what's going on. It's probably we have too many devices on the internet right now. My wife's working at home from now too, and she has like 2 computers set up. So.
I turned my laptop off.
Okay. I heard you the first time. All right. I totally lost track of what I was doing. All right. Let me bring this. Okay. So I wanted to go over next on relative reactivity order. So next slide here is relative reactivity order for acyl substitution. So when we're talking about acyl substitution, remember we were talking about substituting at the carbonyl. We've been doing this all week so far. So I just go ahead and give you the order. The general thing you want to think about is if it has a better leaving group, it's more reactive. And recall back, if you're confused about leaving groups and nucleophilic strength and that kind of thing, you want to go back to 241 and review your SN1 and SN2. We went over that in a lot of detail back during 241, during SN1, SN2. But we saw during that chapter that generally if something is a weaker base or weaker nucleophile, they make better leaving groups. So weaker base or nucleophile are better leaving groups. So if you think about it, if you look at all of the different carboxylic acids and derivatives, they're basically a carbonyl with a leaving group on it. Okay, yeah, it's going to be a little bit laggy. So anyway, the order is as follows. First, the most reactive is the acid halides. So the acid halides are most reactive because you think about it, the leaving group is going to be a halogen. We saw those are weak bases typically. The next type is your anhydrides. Like that. And the next category are the esters. So as I'm going from less reactive going this way. All right, so esters, and then the last one in the set here is your amides, like that. And then for the sake of completion here, I'm going to go ahead and include, as basically no reaction, are your ketones and aldehydes. Let me scroll that up a little bit. Actually, let me just move my face over. That'd probably be easier. Oops. Where is the cam? There we go. All right, slid over. Okay, so your acid halides are most reactive, followed by anhydrides, followed by esters, followed by amides. And remember, these ones, they have no good leaving group, so they have no reaction for substitutions here. So NR for acyl substitution. And the reason why is because they have no good leaving group. And what we saw last chapter, what happens is we get additions instead. So these undergo addition reactions instead. Okay. One thing you may notice is a very notable omission from the list here is that I don't have carboxylic acids listed in the list here. So it turns out that these ones can react under a large variety of conditions. So these ones here react under numerous conditions. And it turns out that if you're trying to make one of these up here, it is actually best if you convert it to the acid halide first and then do a reaction. So best results by converting your COH to an acid halide first. All right. All right. Are there any questions about what we're doing right now? We're just going over a relative reactivity order of the different halides and derivatives. And remember, we're talking about specifically for acyl substitution is what we're looking at. All right, let me see. I think someone's typing. All right, let me keep going. I'll see the question and then answer it after. All right, so what I want to go ahead and do is go over all the different reactions we can do for converting between all the different carboxylic acid derivatives. So let me get my view set up here. So we see, you should have seen this reaction already. There were two different reactions we can do to convert a carboxylic acid into an acid halide. The one here is thionyl chloride. This is SOCl2. Thionyl chloride. What this does here, it converts this to a chlorine. And then the other reaction, we've seen it as PBr3. Yep, PBr3. Or some books show it as PBr5. These are similar reagents. You basically get a substitution for a bromine. So, like that. So after you turn your acid group to one of the acid halides, you can then easily convert it to any of the other derivatives. It just works out where, since that's the most reactive, it's really easy to basically grab whatever nucleophile and do an acyl substitution with it. Hang on, I'm seeing comments, yep, PBr3, yep. All right, so I have just a little another flow chart here for all the different reactions. I'm not doing the mechanisms for all these here. I highly recommend, for practice, you do the mechanism for each one of these that I do. If you know the generic mechanism, these should not be a problem at all. So that's the key thing. You have to know what the generic mechanism is, right? So I'm going to go ahead and use the chloride version as my example here for all of these. And we're going to have a couple different reactions here. So the first reaction here is if you want to get a carboxylic acid, if you want to go backwards, for example, you basically just need water or hydroxide. So H2O or NaOH work here to bring it back to the carboxylic acid. To make an ester, you basically just need an alcohol. So I'm just going to go ahead and use methanol. I thought I closed my email. Hang on. I thought I closed my email. I did. I don't know where that ping came from then. Whatever. Might have been my wife's computer. She had the same email program as me. Anyway, This also requires a base catalyst as well. So essentially what we're doing is everything on the arrows here, these are all nucleophiles. So if you want to keep things straight in your head, this is your electrophile. Everything on here that I'm writing, these are all nucleophiles. So nucleophiles, nucleophile, all these. All right, the next one I want to go ahead and take a look at is for your anhydrides. For this one, all we need to do is throw in a carboxylate. So I'm going to say R prime O minus. So there's your carboxylate. And you'll basically just substitute that out. Like that. And then the last one I have in my set here is for making an amide. So for this example, I'm going to use methylamine. And then for this one, we go ahead and replace. So NHCH3 for that one. All right, so there we can easily see how to make all the other different carboxylic acids and derivatives. Another interesting thing here too is that it's actually pretty simple to convert any of the derivatives back to carboxylic acid. I don't know why I'm getting all these pings here. My email is closed. What is pinging me? My email is closed. Oop. Hang on, I forgot to show my meme. I had a meme ready for today too. Let me show that real quick. There's my meme. Hang on, browser full. There we go. Right above me. Grignard reagents make carboxylic acids. Ain't that cool? Yeah, just Google my memes here. All right. So wrong one. Presenter camera. Okay, so what I was going to do now, I was going to go through some select reactions that I did mention a few minutes ago that you guys really should practice all of these mechanisms on your own. You definitely want to practice these. Yeah, I know I'm a nerd. This chapter is cool. It's so cool. I'm going to say the rest of the screen now how cool this is. You guys started it. I'll blame you for how cool this is. All right, the next thing I want to go over is the synthesis of amides. So this one's a little tricky, so I want to just do some practice here. So synthesis of amides. Like so. All right, so one of the main features I want to mention here is you typically do not start with a carboxylic acid. So typically, do not start with Ku. I'm going to crack myself up here over this Ku thing. Yeah, you're still laughing at me in the comments, I see. All right. The reason why we typically don't start with these is because if you saw in the last picture here, we're going to be using a amine as our nucleophile, and the problem is that amines are bases. Feel free to do so. Feel free. They are super cool. Anyway, I want to show you the reaction. So here we have acetic acid and then reacting with methylamine. So you guys, back in your, chemistry 241, you would have shown this reaction happening. So the thing you can't forget about all your different reactions we've done. They're still in place here. You're getting an acid-base reaction happening here. So we get that, and then we get the aminium salt from this. So here we get our carboxylate, and then here we have our aminium. People also say ammonium here. Ammonium salt out of this. So to avoid this, we pretty much kind of have to convert this to the halide first. Otherwise, all you get is an acid-base reaction happening here. So acid, base, and then some Gen Chem review here, conjugate base. conjugate acid. Remember that 122 stuff? Yep, it's still here too. Same thing happens. All right, so let's go ahead and go through how I would do this. So make myself a little smaller. I'm shrinking.
Wow.
I know I'm a nerd. You're seeing how nerdy I am when I teach. I am totally this nerdy in the classroom too. Don't judge me.
Okay. Not judging.
All right, so SOCl2, chlorine, like that. So the next thing is we then throw in our amine. So if you think about it here, we don't have any acidic H's. So no acidic H's. And we also have a strong electrophile. Okay, so next thing that happens here is your amine comes in. So we're going to use methylamine again, just for the sake of discussion. So we get a nucleophilic attack. So one thing I want to point out here too is in a lot of these mechanisms we're using like H+ catalyst. You typically don't see an H+ catalyst with these ones because they're strong electrophiles, and then your acid is probably in water. So you would basically get a substitution happening here. So no acid catalyst needed for this. All right, so we then have an O-, we have a Cl, we have N. Don't forget that we still had 2 H's on the nitrogen. And the formal charge of nitrogen is now a +1. Okay, we are not done yet. This is our tetrahedral intermediate. Remember I mentioned last time you always have to show this. This is a tetrahedral intermediate. Okay, and so what I'm going to show next is our carbonyl is going to reform. And if you look at these two, so we're looking at chlorine, we're looking at methyl, we're looking at the methylamine. Out of the three, which is the strongest base, or the weakest base? Do we have a carbanion? Yeah, definitely not a leaving group. Carbanions are not leaving groups. Halogen, probably a good leaving group. And then amines. It works out where chlorine is a weaker base and it's easier to leave. So this knocks out. And we're not quite done yet. We have one more little step to go. Like that. Plus. Typically, when you guys run these reactions, you're typically going to run with 2 mole equivalent of whatever your nucleophile is. And the reason why, typically in the mechanism, another mole equivalent of the methylamine will deprotonate. So grab H, deprotonate, and then we are done. We now have our amide. Let me zoom out a little on the camera, guys. I can adjust this. Let me zoom out. Configure, blah, blah, camera control, zoom. There we go. All right. Any questions about the amide synthesis? All right. The last little comment I want to add here, I'll put it in the little corner right here, is that it typically works out you can actually make esters and anhydrides via a similar mechanism. So esters plus anhydrides have a similar mechanism. So when you guys are practicing on your own, you definitely want to try this with esters and anhydrides. You know, when I tell you guys to practice things, you guys know they have a tendency to show up on tests, right? So be aware that I take note of things that I say to practice, and then it jumps on a test. So take my advice, do your homework. All right, I want to go ahead and do one more mechanism with this. So I'm going to show you kind of an intramolecular version of this, just where we have some more challenging practice problems. So what we're going to do here let me get a different. I can still hear you whispering really loudly.
No, I'm gonna stop trying to be nice to you and be quiet.
I don't know. I'm being a little too snarky here at home. Maybe I'm gonna pay for that later. We'll see.
That might be a good thing to stop.
Okay, so here we have this. We're gonna have ammonia. This is gonna be aqueous, so I'm gonna say AQ. And then what's going to happen is a nitrogen is going to replace oxygen. All right, so we have nitrogen, oxygen, oxygen, and we still have one of the H's on the so this was from ammonia, and I want to do the mechanism now for this. So mechanism. Yay. All right, so just like the previous example here, we're not going to use an acid catalyst. Any acid catalyst would mess up with this one here. Remember, that's a base. So if you had acid catalyst around, you're probably just going to neutralize your ammonia. And remember, it's no longer nucleophilic if you protonate it. So what we're going to do here is I'm actually going to shorthand the ring here because the ring is not going to be part of it at all. So I'm just going to shorthand that. Like so. All right. When you first have this nitrogen attack, it doesn't matter which carbon you attack because they're equivalent. So I'm just going to go ahead and have it attack the top one. I'm arbitrarily choosing the top one. Doesn't matter which one you choose. These problems get really tricky. Students have a tendency to lose carbon counts here, and things change willy-nilly. So you definitely want to check carbon counts and that kind of thing while working on these kind of problems. All right, we have that species now. If you're comparing this to the other mechanism, at this point we would do a proton transfer and then make something leave after that. So we need to do the same thing here. The proton is going to transfer to over here. So we go ahead and do a proton transfer like that. And then remember, I'm using this arrow to show that it's a proton transfer step. And then let's draw the result of that. H is now here. We still have a lone pair there, giving a positive charge on oxygen. We have an O minus. We have NH2. Okay. At this point, the leaving group can leave. And if you think about it here, the leaving group is still attached. So it's going to stay attached. So reform the carbonyl. Kick out the best leaving group, which at this point is that group. Like so. And then let me just, I zoomed out so I have more room to write now. So let's go ahead and draw the next step here. So this part here we have an amide. And then over on the bottom portion here we have a carboxylic acid. Like that. Okay, at this point you can show the lone pair from nitrogen doing an intramolecular. Where did the H come from? So we're doing a proton transfer here step here. So the H is from here. This is denoting proton transfer. If you missed my old lecture, that's what that means. So the something else grabs H, something else drops it off. We're shorthanding it with this. All right. So at this point, nucleophilic attack. Like that. We're now going to get. We're now, if you're comparing it to the product, we now have the ring that we're going to be having at the end. So let me scroll up and draw the next part. So nitrogen is now attached. We still have those two H's there we have to deal with. Here is our second tetrahedral intermediate. So you take a look at what's on there. We have an O minus. We have an OH. Does anybody want to take a guess on what happens next? Any ideas on what to do next? Anybody in the Discord, what do I do next? Yep, we need to kick out water. In order to kick out water, you have to first do a proton transfer. Yep, so remember the proton transfers make things better leaving groups. So I'm going to go ahead and do another proton transfer. So I'm going to go ahead and have this oxygen, grab that H, like that, and then I'm going to use my other swooshy arrow there for the proton transfer. We are not quite done yet. So we have an O minus, OH2 plus, one more step and we are done. So form the carbonyl, kick out the Lg. Sorry about the arrows there, they're kind of tight arrows there. But I'm forming the carbonyl, I'm kicking out the leaving group. And then I'm going to go ahead and draw the whole final product here because we're done now. Like that. This kind of compound, I believe, is called an imide. Imide. So not an amide, it's an imide. We're so creative in chemistry, aren't we? It's called an imide. Okay. Are there any questions about this? All good? All right. Yeah, so the next thing I want to do here now is I'm going to show you guys some reactions with amides. And then we're going to do one more reaction after that, and we'll see how I feel if we're going to end the lecture there probably. So let's go ahead and take a look here. So the next thing I want to go ahead and take a look at here is the hydrolysis of amides. So we have hydrolysis of amides. So it turns out that amides are not very reactive. So let's put NR2 like that. So the comment I have here for you guys is amides are not very reactive. And then you also want to remember, if you've taken any biology, these amide bonds in a biology class, you would call them peptide bonds. And if you remember, peptides are basically amino acids held together. They make proteins. So biology chose things to hold together that are tight. So these things don't break easy. So amides and peptides are fairly unreactive. You can actually illustrate that by showing some resonance here. So remember we have a lone pair here. So what you can show happening is resonance with the carbonyl, like that. And then we get NR2 plus O minus. And the main reason why I'm even showing this to you guys is that it turns out that the carbonyl is not as electrophilic. So carbonyl not as electrophilic, or not very electrophilic. Okay, in order for this to for a hydrolysis to happen, the resonance is just like an enolate. That is correct. The resonance is just like an enolate. We haven't got all of our enolates yet, so don't freak out if you don't know what an enolate is. Hi, Tristan. You want to say hi? Hang on. He is not. He is currently not listening, but we'll give him a chance to say hello. Hi.
Hi.
Hi. You gonna say something? No. Give you raspberries. All right. Now go. All right. I lost track of what I was talking about. Anyway, so they're not very reactive due to this resonance here, and in order to get them to react, strong acids or bases needed for hydrolysis. Remember the word hydrolysis means water split. So water split reaction is essentially what a hydrolysis is. They're saying hi, Tristan. Okay, so I'm going to go ahead and show you the generic mechanism here, and then we'll do the general reactions here, and then we're going to go ahead and do mechanisms. Okay, so the first setup here was H3O plus in heat is going to give you that. Take note on how I'm drawing my products here depending on conditions. So it does make a difference. The other side is NaOH in heat. So notice here I'm in acid conditions, so everything is protonated. And then if you're in base conditions, you want everything deprotonated. So you want the carboxylate, O minus, deprotonated. And then we're going to have the ammonia, or sorry, this will be, let me fix my drawing here a little bit, guys. So this should be NH2R2, and then this one should be NHR2 with a lone pair, like that. All right, so I want to go over acid first, then base, and I do want to mention that if we were still going to lab, this would have been the experiment. So this one here is experiment in CHEM 242 lab. I do have a electronic version of this experiment ready to go. I just need to publish it, but it's this particular or is part of it. It's not the whole thing, it's just part of it. So let me add that in there, part of. All right. So first thing I had here was the acid-catalyzed mechanism. This one. So let's just go ahead and say that it's NHCH3, for example. I'm going to go ahead and this is acid catalyzed. Okay, so I just finished talking about how this lone pair is in resonance. So when you're drawing your acid catalyst, you're still going to protonate the same way. So don't protonate the amine group, protonate the oxygen. So have it go like that. And then here, just like we saw in the past, and then NHCH3. At this point, we have an electrophile. You can then do a nucleophilic attack with water. So you have it do a nucleophilic attack with water. We're then going to have a tetrahedral intermediate. You get that plus NHCH3. All right, next step here is we need to do a proton transfer step, I believe. Yep, proton transfer. So right now, this is a poor leaving group. We want to get rid of it because we're trying to get a carboxylic acid. So you're going to take the lone pair and do a proton transfer with it, like that. And then same arrow push. Remember, that's the intermolecular proton transfer arrow. And then what do we have here? We have OH, we have OH, and then here we have, and let me just draw this out so you can clearly see what's going on. Like so. We now have a good leaving group. So all you need to do now is just go ahead and kick out the amine. And then I believe we're done almost. Almost done. Like that. Knock out your leaving group. So we then have this. And then if you remember, when I... Yeah, so the question was, can you use water here to show the transfer? So if you don't want to show the shorthand here, what I would do is have a water pick up the extra H, and then the next step have hydronium drop off the H to this. So yeah, so if you want to show it stepwise, once again you have water grab this, and then a hydronium drop it off in 2 steps. I like to use shorthand. All right, so next thing here is we have that. So once again, I was showing you here the products here. We have a protonated amine. So your amine leaving group, you want to go ahead and use that at the base now. So H2N, CH3, just go ahead and have that. This is probably the strongest base in solution at this point. So have it go ahead and grab the H, and then like that. Oops. So we are now done with this mechanism. Oops. All right. Are there any questions about the acid-catalyzed hydrolysis of an amide or peptide? And this mechanism, at the end, it's coup, right? It's coup. Oh, good goodness sake. I'm going to say this the whole lecture. It's so cool. All right, next one, guys. Let's go ahead and take a look at base-catalyzed. And let's just ask your questions if you have any. I'll answer them for you. All right, just thumbs up. For the next one, I want to go ahead and use your amide that has an NH2 on there instead. For my example. So here I'm going to go ahead and have that. And then the reagent I'm going to use is NaOH. Someone said you're a poor wife. Having to hear my corny jokes all day long. I think by now she's used to my corny jokes, though. I really think she's used to them by now.
That is the darn truth.
What is it? Say it louder.
I said that is the darn truth.
All right, so notice here we are base catalyzed, so you don't want to use a proton here. You are in basic conditions, so no H pluses floating around. This is going to make a carboxylate, this one here. So we are going to go ahead and do nucleophilic attack with the hydroxide, like so. And then we get our tetrahedral intermediate, O minus, OH, and then NH2, like that. At this point, I'm just going to go ahead and reform the carbonyl. I think I showed something the last lecture where I mentioned the poor leaving group here. I think it was with the acetal reaction, I believe, and with esterification, and I showed it grabbing an H on its way out. You could show that here also, because we actually have a poor leaving group here at this point. I'm just going to go ahead and show it this way because you could show it this way as well, where you go ahead and get your carboxylic acid from it. And then what you can show happening here is your leaving group from the previous step just grabs the H. So the equivalent of this is that you show it grabbing it on the way out. Here I'm just showing it leave and then grab it like that. So notice here now I get carboxylate We are in base conditions. This will be deprotonated. So even if you didn't have this, hydroxide would deprotonate. So something's going to deprotonate this if you're in base. And then NH3, and this is actually a gas that comes off. So I want to put a little comment in here. You guys may remember a topic called Le Chatelier's principle back in Chemistry 122. The way we typically see it here in this reaction is that if you have a gaseous product, the formation of the product is definitely favored, because if this is bubbling out of solution, equilibrium is going to keep driving it towards product. So gaseous products drive reactions to completion, and recall Le Chatelier's principle. So once again, the short version here is that if this is being driven off as a gas, equilibrium is going to favor going towards product until all of it's reacted. When we do this in lab, this is actually going to be part of the experiment for the hydrolysis of benzonitrile. We have ammonia coming off as a gas, and the way we actually measure that in lab is we actually put a piece of litmus paper on top, and then if it turns blue with base, that's a positive indicator that ammonia is forming in our reaction. I'm seeing questions in Discord. Typically, NH3 as a product is a gas. NH3, when it's aqueous, is actually reacted with water, making ammonium hydroxide. So yeah, so if you're showing as a leaving group as ammonia, just show it as a gas. Okay. Any other questions about this? All right. So I actually had, so what I think I'm going to do here is I'm going to go ahead and go over the one more reaction. I'm going to show you guys what's coming in the next lecture, and then we'll chat for a few minutes, and I'll cut the stream. We're already at 50 minutes, so I don't want to go too long. All right, so the last reaction here that I want for today is a pretty specialized reaction. This is called decarboxylation. Decarboxylation. This is a very specific reaction. It's basically if you have this type of compound, it turns out that all you have to do is heat this, and then the carbon dioxide will leave. So if you think about it here, if you remember the structure for carbon dioxide, it kind of looks just like a carboxylic acid. You should have remembered that also with the Grignard reaction we did, how we show we can make carboxylic acid from Grignards from CO2. You can do the reverse. The reason why this is a very specialized reaction is this pretty much only works with beta keto acids. Beta keto acids. The way that name is coming is that 1 away from the acid is called alpha, 2 away is beta. So the ketone is at the beta carbon. It's 2 away. So beta keto acids. 1 second, I'm hearing a bunch of questions in the Discord. Let me see what people are talking about. Yeah, this is not so cool. Not so cool. We're losing the coup here. Oh my gosh, I'm cracking myself up here. Maybe I should stop looking at Discord chat. You guys are
cracking so much.
They would be laughing in class right now. They would be laughing in class. All right, so our leaving group is going to be CO2. Our other product is going to be that compound. And for those of you that in Hammond's class probably saw this already, I'm going to go over it in stream when we go over enolates. But it turns out these can tautomerize into this. So I want to mention here that these are tautomers. Tautomers. And what tautomers are is they are compounds that differ by the movement of one atom. So compounds that differ by the movement of one atom. So this is our enol, this is our keto form. So enol keto. So in the case you want to learn a little bit more about this before I officially go over it, I would Google enol keto tautomerism, and you will find the arrow pushes for this. What I want you guys to do on your own is I want you guys to actually try this mechanism, and don't look it up, don't cheat. So I'm going to add that note here, try this mechanism. I want you guys to try it out and try your best not to Google it to cheat. All right, I'm going to show you guys a specific example here for this reaction. So I have a biological compound here. It's fairly large, so you don't have to draw the whole thing out here with me, but you could if you like. Only one part of the molecule is going to react. We got that, and then here we have the Q part is over here. And then 1, 2, 3, 4, 5 carbons, like that. All right, so I want to point out that in this portion of the molecule, if this part tautomerizes, it'll be a beta keto acid. So I'm actually going to highlight this part here. And the comment I want to make is this can tautomerize to a beta keto acid. And then all that happens here is that if you apply heat to this, what will happen is this part will drive off. Only the carboxylic acid will drive off, and in a decarboxylation. Like that. 1, 2, 3, 4, 5. All right. So there is your, and then we have plus CO2. All right. This is one of the cool reactions I'm talking about here. The reason why this is even relevant is because what this actually is. Does anybody know what this molecule is, or the product for that example? The consumption of this was legalized recently in Las Vegas. Well, about a year or two ago. Nobody recognizes it? So this compound is called, yep, you're right. This is tetrahydrocannabinolic, I'm probably misspelling this, acid. This is THCA, and then this one is tetrahydrocannabinol. So tetrahydrocannabinol. I'm probably misspelling the canna part there, but you guys get the point here. This is THC. The reason why this reaction is important for marijuana consumption is because this compound is not psychoactive. Not psychoactive, and this one is psychoactive. So this is actually the main reason why people smoke marijuana, to get high off of it. So for example, if this compound were not, or this compound was psychoactive, you could just eat the raw marijuana flower and get high off of it. But it turns out that if you actually just eat marijuana plant, you don't get a high from it. And some... Not fun, but fun. Is that what I'm reading there? Anyway, what I was getting at here is that in order to actually get the high from marijuana, it has to be heat catalyzed first. You have to decarboxylate it first. So the main way here, you can imagine like someone's putting their smoking pipe here. But this reaction is not cool now, right? It's not cool. But anyway, this reaction has to be heat catalyzed. People do this naturally just by burning it and smoking it, and you get a high amount of THC converted in that process. The other thing too that I'm thinking of is when people make edible marijuana or edible THC goodies, they have to first heat activate this. And if you don't heat activate it first, when you eat that cookie, you're not going to get high off of it. People will typically, what they do is they will take marijuana flower and they will soak it into vegetable oil and then cook it up in a crock pot. They'll heat it up at a temperature enough to decarboxylate the THC, and then they do an extraction process where they remove the plant material from the oil, and then the oil that's left over is then used to go ahead and make your brownies, your cookies, your gummies, whatever edibles that you like to enjoy from the dispensary. But this is the chemistry that's happening there. So out of all the different reaction examples of decarboxylation on the internet, this is probably the coolest one. Right? The coolest one is this one. The DEA is coming. So I want to mention here that anything that I talk about here is perfectly legal to talk about because this stuff is in your textbook. Yeah, I'm teaching you chemistry here. I don't care if it's legal or not, illegal, whatever. It doesn't matter who is talking about it. So unless you're actually doing it, there's no problems here. Figured. Yeah, usually the class erupts in laughter after we go over this one. Officer, it's in my textbook. Yeah. Okay, so I want to state, so if the cop pulls you over and you're smoking marijuana in your car, do not tell them you're studying OCHEM. Do not name drop me on this. That's your call to make, not mine. All right, guys, I'm going to switch over here. All right, so I'm actually thinking we're at a good stopping point for the lecture right now. I did have a little bit more I wanted to go over. We got to give credentials for this. I suppose so. But anyway, I did want to go over a little bit over what we were going to talk about for next time. Let me actually pull that up here. Yes, I am likely doing a stream tomorrow. I will do a stream on the stuff that I'm going to show you real quick. I'm just going to kind of skim through it, and then we'll cut the stream. So, all right. So I'm going to File. And why is it not showing? Hang on, it's not showing. You seeing it now? There we go. All right, so let me zoom in a little bit so you can see it better. So I'm going to go through these notes next time. You scroll. You guys do have it posted on Canvas. So we're going to go over the hydrolysis of nitriles. So the short version of this is we have a nitrile group. These do actually act similar to carboxylic acids in that the carbon is electrophilic. And then here I'm looking about the middle portion here. You actually do get an amide in the middle, right here. And then the rest of it was what we did today. So this last part of the mechanism is the same as what we just did. This is already in the notes. Base conditions are similar. We're also going to go over polymerization reactions, so how to make polyesters and nylons. And then I had a little bit of nomenclature to do still, so we still had to do the nomenclature on acid halides and amides, I think. I typically skip the naming on anhydrides, but they're in the notes. And then I had a bunch of practice problems throughout here I wanted to work on. I'm not going to start lecturing on amino acids yet. I think I'm going to go ahead and reserve the amino acid lecture for Tuesday. And then we will go with enolates after that. Hang on, I'm reading a lot of questions in the Discord chat. Hang on, let me switch over to that. All right, are you lecturing tomorrow? Yes, I'm going to be wrapping up the carboxylic acid lecture tomorrow. I'm thinking around noon, probably. The next question was, does Hammond's class have a test soon? We are going to be doing our test together, and probably after spring break, we'll do the exam. We are going to have a quiz again this next week on carboxylic acids. And then when are you going to stream? Yeah, the quiz that is currently posted is just aldehydes and ketones. For those of you guys that are in my lecture, I am not putting that on the exam, because if I don't put it on the exam, then both classes are on the same page. Hammond already tested on... wait, what am I saying? So you're going to see what's coming ahead here a little bit. So this reaction right here you're talking about, I think. So the first reaction is the nitration, and the second step is how you convert NO2 to NH2. I think Hammond covers that during the amine chapter. I covered it already during the during the aromatic chapter. Yeah, so this is not the Clemenson, guys. So if it's zinc or tin and HCl, we'll convert an NO2 to an NH2. We were actually supposed to do this experiment in lab. This is like one of the last experiments. It's actually in the lab manual if you want to look this up. I believe it's titled Reduction of a Nitro Compound, if you want to just look up the details in there. All right, guys, I'm thinking we are definitely at a good stopping point. I will continue this lecture, pick up this lecture tomorrow, and then I'm going to hang out in the Discord chat for a little while if you guys have any questions about anything. So, all right, with that, I will see you guys later. Thanks for attending. Have a good one. Stay cool.